Welcome back to Mrs. Strauss's chemistry class. Today we cover spring trends on the periodic table. What are the new and hottest trends on the periodic table of elements? So this year, families will be reacting the same way. Well, actually any year they'll be reacting the same way. And I already alluded to this before. Why do elements in the same family react the same way? Because they have the same valence electrons. So in the first group, the alkali metals, they all explode when you put them in water. And hopefully I'll demo this Friday or Monday. And but they all explode when you put them in water. Why? Because they all have one valence electron. Very different experience when you put the alkali earth metals in water. You put the alkali earth metals in water, they kind of bubble vigorously, but they're not exploding. Why do all the noble gases react the same way? They all have the same number of valence electrons, 8. So, same number of valence electrons, you are going to react the same way. Now, when we covered the last chapter, I gave you a handout that showed all the exceptions to orbital filling. And I said that we didn't have to worry about those exceptions. And for the most part, you don't. But there are two groups, the chromium family and the copper family, where the exceptions are, they all have the same reason for that exception. Now sometimes exceptions have an easy explanation, sometimes they have a difficult explanation, and that's the difference between inductive and deductive reasoning. With deductive reasoning, you take a general rule and you apply it to a specific case. That's what we do most of the time in science. For example, as a general rule, juniors have driver's license. Ava is a junior. Therefore, Ava has a driver's license. So that's a general rule applying it to a specific case. Now, what about the opposite? Inductive reasoning. It's where you study a specific case and come up with an explanation. So, example of this, Brittany. So, Lily is a junior, okay? Therefore, she should have a driver's license, but she doesn't. So what do? We pretend Lily just doesn't exist, she doesn't fit into the model, let's stick her in the closet, lock the door, forget about her. No, we have to study her, figure out what is it about Lily and why she doesn't have a driver's license. And the reason why it is because she suffers from spasmodic leg syndrome, where her leg goes Okay? So she is not allowed to drive. So there is a reason for that. Okay? It's not just like, oh, Lily doesn't like to drive. No, there's always a reason in inductive reasoning. But you just have to study that person. I actually, well, who knows?
You what? You knew someone who had that?
I definitely
Maybe you
have it.
have it?
My whole life is a spasmodic syndrome. Yeah. So here's another example. Alicia is a junior, therefore Alicia should have a driver's license. But when we examine her, she doesn't have a driver's license either. So does that mean she has spasmodic leg syndrome? No. Okay? With inductive reasoning, you have to start with the specific case and work back to the rule. Just because Lily had it doesn't mean the same thing's going to happen with Alicia. And when we study Alicia, we find out the reason why she doesn't have a license is because she's legally blind. So she can't drive. So whereas deductive starts with the general rule, juniors have driver's license, it works very good deductive reasoning. Carly's a junior, pretty darn good luck that she's got a driver's license. But every once in a while you run into the exceptions. When you have those exceptions, you study them, find the reason. So for all of these exceptions on the periodic table, there's a reason there, okay? But for most of them, the reason is not the same. Like for the chromium family and the copper family, they have the same reason why they don't follow the pattern. And so I'm going to refer to our little orbital filling sheet here.
Why does W not fit with the...
Well, it does follow the rule.
It wasn't...
Right, because it follows the rule.
Oh, Marty Vance.
I mean, why isn't it doing what it's supposed to do? I'm not sure.
But it's family.
As part of why isn't it doing what the other family? I'm not sure. So if we look at chromium, believe it or not, there are limits to my knowledge. Chromium is argon, 4s2 3d. Yeah, it's AR. There's the R. What's that?
Well, you just drew it.
You totally did that. Just do that.
Come on, I'm having a rough day, guys.
You
Don't
cannot
mess
cheat
with
your
my
way out of
mind.
points. That was a mistake.
So now, when you look at it like this is what we would expect it to be, but that's not the real configuration. The real configuration of chromium is argon 4s1 3d5. That's the real configuration. So now what we have to do is we have to figure out an explanation for why that is. Okay? Now, when we drew the orbitals, the 4s was lower in energy than the 3d. Since it's lower in energy, you always fill the lowest orbital first, and then you start filling the next one. So we fill the 4s2, and then we start filling the 3d. As we fill the 3d, a way to think of it is it drops in energy. As you place an additional electron in there, it begins to drop in energy, and when it gets to 3d4, it actually drops in energy below the 4s. So when you get to 3d4,
Mr. Strauss, for the real one, it's 4s1 35?
yep, that's the real. This is what we'd expect, that's the real. So what happens is the 3d drops below the 4s, and then one electron from the 4s2 falls down into the 3d.
Someone just make that up, or did they actually observe that?
You can't observe it, you can explain it mathematically. Or you can make it up. It's a pretty good explanation though. So that's what happens to chromium. Now, the next electron where does it go? Well, when that electron goes from there to there, then the 4s in turn drops in energy. And so when the next electron goes in, it goes in the 4s. So when we look at manganese, manganese is argon 4s2 3d5. And then it continues normally as we were doing before. Until you get to 3d9, the copper family. When you get to 3d9, the same thing is going to happen as we did with the chromium family. We'd expect copper to be argon 4s2 3d9. But when you get to copper, this drops down. And an electron from the 4s2 goes into here. And so the real configuration of copper is argon 4s1 3d10. So essentially, D4s and D9s don't exist. Because when you get to D4, an electron falls in. When you get to D10, an electron falls in. And so when we were labeling our periodic table, I kind of fudged over this stuff, Allison, but I didn't want to explain it to you right there and then. When you look at the periodic table, we went 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. Technically, the filling goes 3D1, 3D2, 3D3, 3D5, 3D5, 3D6, D7, D8, D10, D10. Because when you get to where D4 is supposed to be, that's when an electron falls in from the 4s. Yep.
So that's like the whole column of D4?
Yep,
Like,
so this would be a D5, that would be a D10, and that would be a D10.
So D4 like doesn't really exist.
So D4 and D10 really don't exist.
You mean D9?
I mean D9. D4 and D9 don't exist. Yep, Melissa.
So you know how you circle
Yep.
and then the one from unit and not UWS?
I'm not sure why tungsten doesn't. I would have thought tungsten would have done the same thing. There's something about tungsten.
So tungsten and SG.
Sigborium.
Sure. We do that.
Correct. But sigborium probably does something else because that's really, when you get down to that 7th row, weird stuff happens.
So tungsten does have a D4 then?
Tungsten does have a D4.
And
And that's where that double fold-out periodic table is nice, because it gives you the real electron configuration below it. So, and that's, I don't know what they'll let you use in college, Haley, but that's a really nice thing to have, to be able to just quickly and easily look up the real electron configuration. So that's the only exceptions that I wanted you to find or to know about. Like I said, for all of these, I could probably figure out the reason why for all of these, but we don't need to do that for all of them. As long as we have those two families, we're in good shape. right? Then objective number, well, we did 1. Now it's number 6.
On our periodic tables, it puts 3D before 4.
That does it. If it isn't, it's typo. 4S1, right there, look. 4S1. Oh, I don't care about that. That's fine. Tomato, tomato.
That's all you just taught us.
People in science don't always, she was saying that, okay, when it's written on the periodic tables you have, they write this as 3D10 4S1. Okay, I've seen it written both ways. I subscribe to that way of writing because I like that because it reinforces then that you fill the 4S before you fill the 3D. I'm afraid if you do it like this, some people will start thinking you fill the 3D before you fill the 4S. So that's why I subscribe to this way of writing. But there are other ways, you know, there's a little, sometimes disagreement in science. You don't always get along. Okay, rules for orbital stability. And really, this is like one of the big things of why we studied quantum mechanics, okay? If you forget everything else, Ailish, this is one of those things, okay, this remember, okay? So, we're going to use these rules to predict charges for things. So, the rules go in order of importance. So the most important thing you want to try to do is have a completely empty or completely full energy level. The whole level.
Like the S, the P, and the D?
Nope, those are sub-levels.
Like, that's what I mean, like all those together? You want all those filled?
Yep, all those filled. So, let me give an example. Suppose we're looking at nitrogen. Nitrogen is 1s2, 2s2, 2p3. If I can gain 3 more electrons, I would have a completely full second energy level. So that would be awesome. So if I gained 3, I'd have a completely full second energy level. Or if I lost 5, I would have a completely empty second energy level. Now electrons, or atoms, they don't like to lose more or gain about 3 electrons. So nitrogen would rather gain 3 than lose 5. So if it gains 3, what is the charge on nitrogen? 3 minus. So that's the reason why nitrogen forms a 3 minus charge. And that's the reason why everything in that column forms a 3 minus charge, is because by doing so, it gets a completely full energy level.
Wait, can you get that?
Actually, I was going to write it on here.
Okay.
So that's right below your... 2. If you can't do that, then try for the next best thing. And that is have a completely full or empty sublevel. Suppose we can do that one. Tin. Actually, that's a good one to do. So tin normally is krypton 5s2 4d10 5p2. Now, if I got rid of the 5 P's, that means I'd have a completely empty P sublevel. To show you on here, it could look like this. So if I get rid of these two, now I have a completely empty P sublevel. So that's also good. I mean, there's no way I'm going to get enough electrons to fill the whole 5th energy level. So just by removing those two and having an empty P, that's good. So that would give me tin with a 2 plus charge. Nope, it's not negative. Because it's below the staircase. It's a metal. Metals form positive charges. Now you're probably looking at that, Kenzie, and thinking, well, wait a minute. You just explained how I lose that sublevel, but why not just get rid of the 5th energy level altogether? Get rid of the 5p, get rid of the 5s. Just go ahead and erase those guys too. Get rid of them. Then the 5th energy level is completely empty. That's following rule number 1.
I thought elements didn't like to lose or gain more than
It gets a little bit iffy. You know, 3, 4, 5, like tungsten will lose 5, I believe. But for the most part, like most electrons, plus or minus 3. Most atoms, plus or minus 3. There are a few that will do more than 3. So here, I got rid of the whole 5th energy level. Here, I got rid of a sublevel. So which do you think tin would like to do more of? B plus 4 or plus 2? Which one is the better rule, 1 or 2? One's the better rule. Which one gets rid of a whole level? Plus 4. So tin prefers to be a plus 4. You'll do the plus 2, and that's why, Ms. Rosenbaum, if you go to your appendices, you'll see that tin forms 2 charges. That's the reason why. Now you know the rest of the story. I know you've been wondering about that since day 1.
Since day 1.
Since I talked about the ones that have multiple charges, and that's the reason why. Kind of exciting. It is semester 2. Semester 2 is explaining semester 1. Last rule. Have a completely, not completely, have a half filled sub level. That would be also good to have. So you try for 1. If you can't do 1, you try for 2. If you can't do 2, try for 3. And an example of this is iron.
What if you can't do 3?
If you can't do 3, then the thing probably, you should be able to do 1, 2, or 3. If you can't do 3, then I'm guessing it's a noble gas, and it won't do it regardless. Okay, iron is argon, 4s2, 3d6. So if iron gets rid of that 4s2, I just got rid of the whole 4th energy level. That would be following rule number 1. So there, iron forms a +2 charge, just by getting rid of the whole 4th energy level.
And that's rule number 1.
That's rule number 1. But here's another thing iron can do. If I go over here and show it on the picture here. So I got rid of that 4s2, but I can also get rid of just 1 electron there and have a half-filled D. So if I get rid of 1 of those, I could, actually let me do it from up there. If I get rid of 1 of those, I get iron 3+, 3d5.
Did you burn your beer?
I combusted it. So,
Just because he can't.